Good morning. In today's class, we're going to be discussing a couple of nuclear processes. So we're going to continue on from our discussion last time about the kinetics of nuclear decay and sort of focus more today on a specific process that's related but not the same as nuclear decay. And we're going to do that over the next couple classes. Today we'll focus on nuclear fission, and in the next lesson we'll focus on nuclear fusion and other types of nuclear reactions. Okay. So these are not specifically decay process, these are other nuclear processes that can occur. So kind of up front, the difference between fission and fusion. So nuclear fission, right, is when a large nuclear splits into two smaller nuclei, typically via a reaction with a neutron. So the word fission is coming from the use of the term fissure, right, a crack that develops like in a rock or something. So it's the splitting apart of the nucleus. So when we say split the nucleus or splitting of the atom, right, we're just referring to nuclear fission. Nuclear fusion is two smaller nuclei coming together, or colliding together, smashing together, sometimes called, to make a larger nucleus. So we're fusing two smaller nuclei into a larger nuclei, and that's nuclear fusion. Both of these processes release tremendous amounts of energies, right? Fusion actually releasing more energy per gram than fission does. Now, the biggest thing typically associated with these types of nuclear reactions are nuclear weapons. So we will discuss some nuclear weapons. I will point out some videos that I've posted on Talon for you to watch about nuclear weapons. And then we will also talk about some other aspects where we can use these nuclear processes like energy, etc. So the picture here is the first nuclear weapon tested in the world, right? This was, the U.S. was the first to develop nuclear weapons, developed in the course of the Manhattan Project in the early 40s, and that sort of culminated in the test in the New Mexico desert dubbed the Trinity Test on July 16th, 1945, when the U.S. tested its first nuclear weapon. So we'll talk a little bit about this test as we go forward. It had an explosive yield of between 15 and 18 kilotons, or KT, right? So if we think about, power, right? So this was what I referred to as, I'll just call it 15 KT. It ranges, when you see sites, between 15 and 18 kilotons. Now, what this means, what KT means here, right, is kiloton, or the equivalent of, in this case, 15,000 tons of TNT, right? So this is how we rate these nuclear weapons, is the explosive power comparative to dynamite, or TNT. So this had an explosive power of between 15 and 18,000 tons of dynamite, or TNT. Okay. Now, not every nuclei will undergo fission, right? You need specific isotopes to undergo fission. They're what we call fissionable isotopes. So one of the most common fissionable isotopes is uranium-235. Now, we've talked about uranium, or uranium isotopes in other ones, like uranium-238. It's a very abundant uranium isotope. It is non-fissionable, right? It cannot undergo fission. So only certain isotopes are fissionable. Now, natural uranium contains less than 1% uranium-235. So the vast majority of uranium is uranium-238, which is still radioactive, but it cannot undergo the fission process. Now, in natural uranium, there isn't enough uranium-235 to actually cause a nuclear process to occur, right? To cause a chain reaction to occur. You need a higher percentage of uranium-235 for this to happen. So, in order to create fission, right, to create what we call a fission chain reaction, you need to have enriched uranium. Now, what that means is that by a process, they've enriched the amount of 235 in a natural process, typically by, concentrating the uranium-235, right? You're removing the uranium-238 or separating the 235 from the 238, at least partially, to create what's known as enriched uranium. So this all started back in the 1930s with Enrico Fermi, right? And he was doing neutron bombardment experiments of uranium-238 to try to synthesize heavy elements, right? So he was trying to talk about another process that we'll talk about a little bit later, which is transmutation, right? Changing one nucleus into another by bombarding it with something, right? So he was trying to create heavier elements from lighter elements with neutron bombardment, or essentially shooting neutrons at these lighter nuclei to try to make heavier nuclei. Now, so Fermi was initially doing these experiments, right? And he attempted to do this. And it's believed probably that he actually identified saw the first nuclear fission. Now, he didn't actually bother to characterize the products of what was going on, so we don't actually, credit him with that discovery, but sort of kicking off this process. Now, it was in 1939 that two researchers, Lisa Meitner and Otto Hahn, repeated and identified the lighter elements that Fermi's earlier experiment had created. And so this goes down as the first report of nuclear fission, January 6th, 1939. And if we think about what's happening here, is we're taking a uranium-235, right? Which again, there is a small percentage, less than 1%, right, of uranium-235 in any sample of uranium. And so that gets bombarded with a neutron, and you get the fission. You get the breakdown of the uranium into a barium nucleus and a krypton nucleus, along with 3 more neutrons and a whole lot of energy. Now, one thing I want to point out right here is the creation of the 3 neutrons, right? So these 3 neutrons can go and seek out other atoms of uranium-235 and do this same fission process, each time creating 3 more neutrons, which can potentially collide with other atoms of uranium-235. And this is how we can create potentially a fission chain reaction, where we get an accelerating process, where we get more and more nuclei undergoing the fission process. So a chain reaction occurs when a reactant in the process is also a product of the process. So we have a neutron as a reactant, we're creating 3 neutrons in the process, and these products then get recycled and become reactants. So we don't need a whole lot of neutrons to start with if we can get that chain reaction to propagate. It's what we call a self-amplifying reaction, right? Because we get 1 neutron, we potentially get 3 out. And each of those three could potentially get 3 more out each time. So we can go from 3, 1 creates 3, those 3 can potentially create 9, those 9s can create 20, and you see how that could keep going on and on and on. Now, to actually get this chain reaction to occur, you need a minimal amount of the fissionable isotope of the uranium-235 needed to sustain that chain reaction. And this is what's called the critical mass of the fissionable isotope. So in order to actually get one of these chain reactions to occur, you need a critical mass. So this is why, Fermi and Meitner and Hahn didn't see these sort of nuclear explosions, fission explosions, because they didn't have a critical mass. Right? They didn't have enough uranium-235. They typically had natural uranium, which again contains a small amount of uranium-235. So if we sort of analyze the chain reaction here, again, we can see the process. So each time we get a fission, we create these smaller nuclei and 3 neutrons. And so again, we've talked about it, how this can amplify, and that every neutron creates 3 more neutrons, and so forth and so forth. And so we can see how this could just keep expanding, creating more and more energy, right? Each time this happens, we get energy output. And so that amount of energy just keeps going up and up and up during the process. Now, if we talk about nuclear weapons, right, the atom bomb, as it were, right, people were starting to worry about this right at the outset, right? As soon as, scientists got wind of these results coming out of Fermi's and more so Hahn's and Meitner's experiment, right, they immediately saw the potential here, right, that this could be weaponized. If you could create one of these chain reactions, that you could create a weapon. And that prompted a 1939 letter from Einstein to President Roosevelt warning about the potentials of Fermi's and other people's work in the development of weapons, coming at the time, of course, of the Nazi, build-up in Germany and expansion in Europe. And there was, maybe real but also elevated fear that the Nazis would develop this weapon first. And so he encouraged the U.S. To take this path. And you can see a text of at least part of this letter in the textbook, where it sort of encourages Roosevelt to act, to, either create one or to figure out if the Germans were creating one. Now, we all probably know the history that this led to the development of the Manhattan Project, starting in 1941, run by Oppenheimer, with lots of other scientists contributing to this. And over the course of 4 years, roughly, we went from theoretical idea to weapon test, right? It is sort of truly amazing, based on, what was available at the time and the knowledge about this, which was extremely limited, how fast that they were able to do this. It just shows when you put the right people with the right resources, enough money, right, what can be done here. Now, a lot of this work was done all over the country. A lot of it was done in Chicago, right, in the Chicago area. We're familiar with Fermi Labs, perhaps, which is a national lab where they still do different kinds of nuclear reactions in a cyclotron. But University of Chicago was one of the heavy research places that led to, or that was doing the initial testing that led to the actual atomic weapons test that took place in New Mexico. Now, as I mentioned at the beginning, that first nuclear test, the so-called Trinity test, was conducted on July 16th, 1945, with a yield of, again, around 18 kilotons, 15 to 18 kilotons weapon. And this is a massive explosion, right? I have a video on Talon, one of the videos that I expect you to watch, that looks at this first test and talks about, how people were thinking going into this test and the fears and, the unknown about what was going into this, right? That was a plutonium-239 device, right, based on another fissionable isotope, plutonium-239. Soon after that, less than 2 months after that, the first atomic bomb was dropped on Hiroshima. It had a yield of about 15 kilotons. That was a uranium-235 device known as Little Boy. And 3 days later, the bomb was dropped on Nagasaki. That had a slightly larger yield, up to 20 kilotons probably. That again was another plutonium-239 device known as the Fat Man. Those names, and you can look up on the internet, come from the shapes of those bombs. So, we talked earlier about the critical mass. And the critical mass for at least uranium weapons is about 50 kilos, or about 50 kilograms, of 85% enriched uranium-235. So, you have to have very enriched, right? Remember, natural uranium is about 1% uranium-235, and so it has to be enriched up to 85% uranium-235. Now, we'll talk later a little bit about nuclear energy. The nuclear fuel used in nuclear energy is not what we call weapons grade, right? It is not enriched up to 85%. It is enriched, but more like 20% uranium-235. The largest nuclear bomb or atom bomb that's been tested was the Tsar Bomba device, tested by Russia in the early 60s, 1961, which was the largest nuclear test ever conducted. Hopefully will be the largest nuclear test ever conducted, with a yield of about 50, not kilotons, but 50 megatons, right? And so just review, remember megaton, right, is 1,000,000 tons, right? Mega, 10 to the 6th. So this bomb had an explosive power equivalent to 50 million tons of TNT, right? Many, many, many times more than what the bomb dropped on Hiroshima and Nagasaki were. Remember, those are 15,000 tons. This is 50 million tons. So, many, many, many fold more powerful. So, I can talk more about nuclear weapons here. Before I do move on, I do want to mention a couple of other things. That I do have a couple more videos that I want you to watch on Talon. There is one there, and these are in the Chapter 21 Nuclear Chemistry folder under Unit 4. There's one on the Trinity test. There's one that recounts the bombing of Nagasaki. So you can get a little background there. And also one that talks about that 50 megaton bomb, the largest ever tested in the world, that was done by Russia in the 1960s, 1961, called Tsar Bomba. Just a little historical context, 1963, right? The presidents of Russia and the U.S. Outlawed nuclear testing above ground, below ground, underwater, and in outer space. So there's also another video up there called the Castle Bravo nuclear test. You'll hear it when you see it, but the Castle Bravo represents another kind of nuclear device. This is a nuclear fusion device, somewhat typically called a hydrogen bomb, right? So while Tsar Bomba and the Hiroshima and Nagasaki, right? These are traditional nuclear weapons. The Castle Bravo test, which took place in the 1950s, was what we know as a hydrogen bomb, or sometimes called a thermonuclear weapon. So we might come back and talk a little bit about nuclear weapons later on, but I want to move on a little bit now and talk about another aspect of nuclear fission, which is nuclear power. So that same energy that is released in a nuclear fission that can be harnessed to create a nuclear weapon with an uncontrolled chain reaction, right, can also be used in a more controlled way to create nuclear power. So let's talk a little bit about what we mean when we say nuclear power. So nuclear fission, in the sense of nuclear power, is a source of energy. In this case, mostly heat, right? Essentially speaking, the heat or energy produced by the fission process in a nuclear power plant is used to create steam. In many ways, the same way that in a coal power plant, the burning of coal is used to create steam. The steam ultimately then is used to create the electricity in a generator. So the nuclear reactors use fission to create steam, which is ultimately turned into electricity. Now, the count varies a little bit depending on time, but about 20% of the U.S. electricity comes from nuclear power plants. That can be upwards of 70% in certain countries. But, the U.S. is quite low. Now, a lot of people believe this stems from the incident that occurred in 3 Mile Island, which was not a core meltdown per se, right? It was not a nuclear sort of huge nuclear release there. There was very little actual release into the environment, but it was a partial core meltdown that led to a lot of anti-nuclear sentiment in this country. And so we've sort of stabilized at that, there hasn't been a huge amount of investment or creation of new nuclear power plants since that incident occurred. So just to look at the layout here. So if we think about there being sort of two parts of a nuclear reactor, we have the nuclear part, where we have the reactor, right? And the reactor here being made up of the nuclear fuel, which is the fissionable material, what we call fuel rods. These rods contain pellets of nuclear fuel, uranium, really common one. Contains what we call control rods. We'll talk a little bit about what these are used for, but control rods are used just to control the reaction. They're used to absorb neutrons, which eliminate the ability to get into a chain reaction or an uncontrolled chain reaction. And this heats up water, and that water is passed through, right, this superheated pressurized water, into the generator, right, where we have a separate water supply, right? Which comes into here. This super heated water converts that into steam, which then goes out the top and goes into the turbine, which creates the electricity. So we can see there's two separate water supplies, water systems here. There is the nuclear system, which is radioactive, and then there is the clean water system, right? So what if we compare nuclear energy to other energies? And I will preface this by saying that this is not a political statement. This is not saying one is better than the other, right? All forms of energy creation have issues, have problems. It's just a matter of what problem you want to deal with. So, one of the advantages that nuclear energy has is how much material it takes. So, in terms of the amount of energy that you can create in a nuclear plant, you use about 50 kilos of fuel. So, about 50,000 grams of your nuclear fuel will create enough electricity for about 1 million people. Whereas in a coal plant, we require about 2 million kilos of fuel, of coal, to generate the same amount of electricity. So your raw materials, much less. Right? There is, of course, the issue that, raw materials run out. And that goes for both cases, but we're going to use that coal a lot faster than we're going through the uranium here. Other advantages of nuclear fuel, no pollution, right? In terms of air pollution, in the classic sense of releasing nitrogen oxides, sulfur oxides that contribute to acid rain, or carbon dioxide that contributes to global warming greenhouse effect. Okay. Now, what nuclear energy also has maybe in its disfavor is the threat of, quote, nuclear incidents or nuclear accidents. We also have what's probably the biggest issue with nuclear energy, and that is disposal and or storage of the nuclear waste that is created. Now, the problem with that is that, if you remember from before, right, a lot of these nuclear isotopes, these spent nuclear fuels, contain radioactive isotopes that have extremely long half-lives. Right? So they're going to be with us for a long, long time to come. That means we have to have some way to store them so that we're not going to expose something to this radiation. Now, so if we dive a little more detail into the core, I said we're going to have these fuel rods with the fissionable material. Now, as I mentioned earlier, right, these fuel are what we call subcritical. They are about 3.5% uranium-235, right? So much less than what I mentioned earlier for weapons grade, which is 80 and above, right? 85% is what I mentioned before, right? So these are not weapons grade. These are subcritical. You can't get a chain reaction that would lead to what we might consider a nuclear explosion like you see with a nuclear weapon. What you can get is a core meltdown and release of nuclear material into the atmosphere. Typically, an explosion that occurs in a core meltdown is coming from, say, hydrogen gas building up and exploding, or something like that, or steam, or these kinds of things. So, again, there's also the presence of control rods, right? These are made of neutron-absorbing materials, usually a boron or cadmium, and these absorb that neutrons, right? They control the chain reaction, right? Neutrons are needed to sustain it, So we want to control the fission and not let it become a runaway chain reaction. And then furthermore, the rods are placed in a bath. Typically, this is a solution known as a moderator that it allows a controlled reaction to occur. It generates the right amount of heat needed for electrical generation. Not more, not less, right? Now, as I mentioned, we have issues that occur. The first biggest issue, right, is core meltdown, right? This is the things that can lead to exposure of nuclear materials into the atmosphere. So typically this is caused by water loss from the core, so that moderator, that water that the rods are in, that evaporates away, right? The heat then builds up and eventually reaches the melting point and melts down the core. So I mentioned 3 Mile Island in 1979. This was a partial meltdown. Some release, but very little effect, very little impact on the environment and the people. Now, there was Chernobyl in 1986, which had huge repercussions in terms of the amount of radioactive material released, traveled all around the world in the atmosphere, left hundreds of thousands of people displaced, and led to large swaths of land being uninhabitable for long periods of time, still up to this day, really. That most of that area is not fit for human habitation. And then, of course, we had Fukushima in 2011. Right? Now, especially with Chernobyl and Fukushima, we'll focus on Chernobyl, but these core meltdowns occurred for not as an inherent danger of nuclear power, but of confounding issues that created a problem, right? It wasn't just one thing that went wrong. It was a chain reaction of things, if you will, that went wrong that led to a meltdown. Now, I've posted a video on Talon that I'd like you to watch about Chernobyl, which discusses that particular incident and what maybe led to it and some of the aftermath of that incident. Now, as you can see, that's only 3 incidents and really 2 incidents that we can really point to in the history of using nuclear power. So it is, while a real concern and could be devastating potentially, right, not extremely likely, right? As many nuclear power plants that are running, the number of incidents is extremely small. But of course, what I think is the bigger issue is what do we do with the waste that is normally generated, right? It's highly radioactive. Can we reprocess that? Do we have to store it? And where do we store it, right? And so we still don't have a satisfactory answer to this in the U.S., right? One of the latest efforts was to store it at Yucca Mountain in a salt mine in Nevada. That never was approved due to various protests and different things. And so we're still ultimately looking for a home for the nuclear waste. In this next section, I want to look at how nuclear fission produces all of this energy, right? So we talk about all of the energy that's created by nuclear fission and also nuclear fusion, but how do we create that energy? Well, essentially, we're coming down to Einstein's famous equation, E equals mc squared, right? Where some of the mass of the nucleus is converted into energy. right? And so we get energy equals mass times the speed of light squared. Right? And so for each mole of uranium-235 that fissions, we produce about 1.7 times 10 to the 13 joules of energy, or 17 billion kilojoules. So think about that a little bit, right? Uranium, right, element 92, has a molar mass of about 235, right? 238 if we look at just normal uranium. But if we think about uranium-235, so about every 235 grams of uranium-235 will produce 17 billion kilojoules. Now, just to keep that in context, an extremely exothermic chemical reaction that we've talked about might produce 1 million joules per mole. And most, not even close to that. We're talking, not that many. So, lots and lots of energy coming from this conversion of mass into energy. Now, why do we see this, right? What's the issue here? Well, or how do we get this conversion? So if we look at the breakdown of uranium-235 plus a neutron breaks down into a barium and a krypton nucleus plus 3 neutrons. So if we add up the sum of the masses of our reactants, so the mass of the uranium-235 isotope is 235.04392 AMUs. Mass of a neutron, 1.00866 AMUs. So we have total reactant mass of 236.0528 AMUs. If we look at our products, right? A barium-140 isotope has a mass of 139.910581 AMUs. We have a krypton-93, which has a mass of 92.93113 AMUs. And 3 neutrons, so giving me a total product mass of 235.86769 AMUs. And we can clearly see there's a discrepancy here. We've lost mass. And so we can calculate that loss of mass as 0.18489 AMUs. Well, that doesn't seem like a very large amount of energy per se, or mass, I should say. But if we take that mass and we convert it into kilos, right? So there's 1.66 times 10 to the negative 27 kilograms per AMU. So the mass loss in kilograms represents about 3 times 10 to the negative 28 kilograms. So then if we look at Einstein's equation and think about how much energy that might be, if we take our mass loss and we multiply it by the speed of light squared, we get the creation of 2.7 times, or 2.7593 times 10 to the minus 11 joules. Well, one might look at this number and argue that, oh, that's so tiny, right? That's to the minus 11. Right? But remember, that is for 1 atom of uranium-235. So if I take that amount of energy and I multiply it by a mole, so it should be raised to the 23rd, right? 6.022 times 10 to the negative to the 23rd. Then we start to see the staggering amount of energy, right? The 1.6617 times 10 to the 13th joules per mole. All right, so 1 mole of uranium produces 1.66 times 0.17 times 10 to the 13 joules of energy, or about 17 million kilojoules. All right, so remember, a joule, a kilojoule is 1,000 joules, billion is 10 to the 9th, all right? And so we convert that, this equates to about 16.6 billion kilojoules per mole. So a large amount of energy, right, for 1 mole. So I want to look at sort of a related topic here, which is the binding energy. So look at this, how this mass defect ties into something called the binding energy. So when a nucleus forms, some of the mass of the separate nucleons is converted into energy. So when we think about all of these nucleons coming together, the protons and the neutrons come together to form that nucleus initially, some of the mass is converted to energy, right? It's an exothermic process. In this case, that energy is coming from mass conversion into energy. This leads to what we call a mass defect, where the mass of the atom is not exactly the same as the mass of the particles added up. So if I add up the mass of the neutrons and the protons, it does not equal the mass of the nucleus. This is called the mass defect. Now, the energy released when the nucleus forms is called the binding energy. Now, the units here are sometimes confusing because typical binding energy units are given in mega electron volts, or MeVs. Now, 1 mega electron volt is equal to 1.6 times 10 to the minus 13 joules. Okay. So these are just units that are sometimes given off. So 1 AMU mass defect is equivalent to 931.5 MeVs. So for every AMU in the mass defect, I have 931.5 MeVs of energy that can be associated with that. So the larger the binding energy per nucleon, the more stable it is. Now, of course, this might make sense because if it has a higher binding energy, that means it's going to be harder to break it apart. Right? And so the more binding it is, or more strongly bound the particles are to each other, the less likely they are to undergo decay, right? To actually lose, to break apart. So let's look at another reaction. Let's look at a specific decay reaction. So I have the decay of hydrogen into helium, right? So I have this process of two hydrogen atoms combining with two neutrons to come up with a helium nucleus. So if I look at the mass of the reactants, right, and the two neutrons, the two hydrogen atoms, right, and I look at the mass of a helium, right, 4.00260 AMU. So the mass defect here, right, is 0.03038 AMU. So the mass of this helium nucleus is not the same as the sum of the mass of the particles that make it up. So essentially the two protons here, right? Remember, this is a proton. And the two neutrons, right? The four particles in the nucleus have a mass of 4.03298, the actual nucleus that contains these only weighs 4.00260. So somehow we lost, or somewhere along the way, we lost this 0.03 AMUs. This is equivalent, if we go via E equals mc squared, that's equivalent to a binding energy of 2.731 times 13 joules per mole, right? Or about 2 million kilojoules per mole. Okay. So what that tells me, right, is that, that helium nucleus is pretty stable, right? It has a pretty high binding energy. So if we look at these numbers in a little bit different way, so I want to go back and make a correction here. I looked at my math again, and I think I had an incorrect exponent here. It should be 2.731 times 10 to the 12th joules per mole, I believe. And this is one way to look at the binding energy, right? It's a large amount of energy. But I said earlier that typically we often talk about, or nuclear physicists talk about the binding energy of nucleuses in mega electron volts, or MeVs. So it's useful, I think, to quote this number in mega electron volts as well. So if we take this same mass defect, 0.0308 AMUs, and we use the conversion between mega electron volts and AMUs, 931.5, we get an equivalent of 28.3 mega electron volts in terms of energy. Now, to make it easy to compare different nuclei to each other, we typically standardize this in terms of a per nucleon value. So in other words, a per atomic particle. So since helium here, our product, has 4 nucleons, if we divide this by 4, then the helium has a binding energy of 7.075 mega electron volts per nucleon. And so this gives us a way that we could compare or standardize the reporting of these binding energies so that we can compare the binding energies of this nuclei versus this nuclei. Now, so this comes down to then looking at a table or a graph of different nuclei and see what this tells us. So if we look at the mass number and we look at the binding energy, right? So we saw that helium was up here with a binding energy around 7. Right? Now, binding energies peak out around iron 56, where we get binding energies on the order of 9. So this binding energy curve maxes out at iron 56 with about, a little bit above 8 mega electron volts for binding energy. Now, in this area, that's where we find our stable nuclides, right? So if we look for isotopes that have lower binding energies, so binding energies per nucleon of less than this, then this is where we see nucleons that are able to undergo fusion, right? So a lot of our very light nuclei are where we see fusion occurring, right? So whether this is the reaction powering the sun or other fusion reactions, right? Now, it's when we get on the other side of this stability that we start to see the processes that we've looked at so far, where we see isotopes that have the ability to undergo fission or potentially fissionable isotopes, things that have, large mass numbers. And we get these large binding energies. Now, okay, so I just want to close out this section on mass defects and where this energy comes from in nuclear fission, and as we can see, and also in nuclear fusion, by looking at a problem to calculate the mass defect and the binding energy for a particular isotope. So the isotope that we're looking at in this problem is carbon-16. This is a radioactive isotope of carbon that has a mass of 16.014701 AMU. So the first thing here is to calculate the mass defect. So we know the mass of the nucleus, so now we need to copy the mass of the individual particles that are in it. So carbon-16 would be made up of 6 protons, and 10 neutrons. So each proton has a mass of 1.00783 AMU, and each neutron has a mass of 1.00866 AMUs. So if we add that together, we get the mass of the individual ones. So just to come up with a number there, so 1.00783 times 6 plus 1.00866 times 10 . We get a mass of 16.1338 AMUs. And if we subtract the mass of the actual atom, 16.014701, we get a mass defect of 0.118879 AMUs. Okay. So we got a mass defect of a little over 0.1 AMUs. Now we want to convert this into a binding energy. Okay. So the second part is to calculate the binding energy. In mega electron volts. So the way we do that is we simply convert our AMUs into electron volts. And we get 110.74 mega electron volts. And if we do this per nucleon, right, 16 nucleon, we get a binding energy that's equal to, or binding energy per nucleon, that's equal to 6.921 mega electron volts. So, if we look back at our table here, so carbon-12, which is pretty stable, right, has a binding energy of about 7.4, right? So we can see that our isotope at 6.9 is going to be less stable than what we know as a non-radioactive isotope of carbon-12, which has a 7.4 per nucleon. Now, and it doesn't take a whole lot more to get around this because, if you were to do the same thing for carbon-14, you get a little bit higher than this. This is more radioactive than carbon-14. That one's about 7.3. So there's not a huge difference between the binding energy per nucleon of carbon-12, which is very stable, and carbon-14, which isn't radioactive, right? Basis of carbon dating. This one is even more radioactive. And so this is the idea of how that binding energy. And so when we look at tables and we see that a mass of an element, right, of an isotope seems to be less than the atomic number, right, or less than, even if we were to assign them a mass of 1, right, then what that's telling me, that's what that is giving me the mass defect, right? And so that's not surprising that if we were to just think about the number of nucleons, that often the mass of the nucleus is not even the same as that number, again, because of this mass defect. And, it is the energy that comes out of this, right, that allows the nucleus to stay together, right? So the bigger that mass defect is, the larger the binding energy is, the more stable the nucleus is going to be.